So hello Internet and welcome to SyC Chile. Our guest today is Nicolas Meirhaeghe, Ph.D. candidate in neuroscience at MIT. Hi Nico.
Hi everyone.
How are you doing?
I'm pretty good.
So would you like to introduce yourself a little bit?
Sure, so as you said, my name is Nicolas Meirhaeghe. I'm a fifth year Ph.D. student at MIT, and I'm in the department between Harvard and MIT called Health, Science and Technology. And so my main research area is in neuroscience. So I was trained in aerospace engineering from France. So I got a master's in Super in Toulouse. And then after that, I decided to go into neuroscience for my PhD.
So that's very unusual. How do you go from engineering to neuroscience?
Yeah, so it was quite of a jump. But basically, I did a project in Super where we studied the sort of cognitive aspects of being a plane pilot and how you can really quickly become overwhelmed by the stimuli around you, and how this could affect your decision making and performance as you're piloting the plane. And so this first project really introduced me to neuroscience in general. And then I took some classes afterwards, and which really propelled me to this next transition.
So today we are going to talk about neuroscience, consciousness, and humans in space. I'd like to start chatting about the challenges that humans have to face in space. When did we first notice the negative impact of spaceflight on humans?
Yeah, so I think it really started at very early days, even before 61, even before we even sent someone into space. I think we realized that airplane pilots have really huge issues, and people thought that probably those issues will also apply when we send someone into space. So really the early years of sending people to space was to quantify and characterize how the human body would react to, let's say, an acceleration while you're taking off. These were really the beginnings of humans in space. As years went from Gemini to Apollo missions, where the missions got really longer and longer, we started seeing new challenges, and so astronauts started reporting sort of perceptual illusions were the first things that people observed, but also cardiovascular issues or bone issues. And so these are really interesting phenomena that there's an interesting physiology to go into. I don't know if you want me to go into the details, but there's really a range of physiological problems that emerge from being in space.
And so which one is the most fascinating to you?
So I think, well, definitely now that I'm interested in brains, I think the effects of being in space where basically there's no up and down, everything is isotropic, if you want. Whereas on Earth, we're kind of bound to a two-dimensional surface where there is up and down, which helps us kind of being anchored in the space. In actual space, outer space, we lose this reference, and as a result, there's a lot of perceptual changes, motor changes. That is to say, we can't do the things that we normally do on Earth, and that is really the aspect that got me thinking about neuroscience in space early on.
So how do humans and animals in general orient themselves on Earth?
Yeah, so on Earth, we have really a set of senses that we use to orient ourselves. The obvious one is vision. So we look around and we are able to use the cues around us to be able to tell where we are and how we are oriented with respect to the world. That is the first thing. Then we have the vestibular system, which people call the sixth sense. And that's really sort of a combination of an accelerometer in your head and a gyroscope, which basically tells you if you're accelerating in some direction or if you're rotating in some other direction.
So where is the vestibular system located? Is that something in your brain, in your ear?
So the vestibular system is located in your inner ear, but all of the signals that the vestibular system records are sent to the brain, and then they're being compared to the other signals, including those from your visual system. So really the I think if I had to summarize the issue of being in space for the brain, is that when you're on Earth, all of the signals that you get from all of your senses, they're calibrated and they're all in agreement, because we know that if we see something moving, that's probably because we are moving. And so these two signals are kind of exactly in agreement. When we go into space, we have information which is in contradiction. Some systems tell you that you're moving, and your visual system might tell you not moving.
So it's a little bit like when you're in a boat and the boat is moving, but you're inside and you don't see things moving around. Right?
Exactly. So it's almost like that. It's almost like the opposite situation. In a boat, what usually happens is that you're inside the cabin, you're moving because the boat is moving, but your vision tells you that you're not moving because you're stationary with respect to the room. In space, it's the opposite. You might be moving, but visually you know that you're moving, but your vestibular system is not recording this movement, or not exactly as it should, because of the lack of the effects of gravity. And so you create a contradiction in your brain, which can cause a lot of issues.
Axis.
Yeah, I'm not sure I could even control it.
Yeah, no, don't worry. Provocative's fine. Just keep it going.
Go faster?
Yeah. Let's go for it.
I was very curious about this notion of orientation in space. And so I designed an experiment where we focused on a very specific case of orientation, which is called the ability to take the perspective of someone else. So that's something that really requires you to reorient yourself in your mind and to take a different viewpoint in the world. And then to ask yourself, what would I see if I were to be sitting or standing there? So that's something that really requires orientation. And so the question was, is this ability affected in space? So we designed an experiment where we asked subjects to do a collaborative task. So basically people were in a virtual reality environment with goggles, and what they could see on the screen was a shelf. So the shelf was kind of floating in space, and there are different objects in each of the units of the shelf. And then there was another character, a fake character, behind the shelf, which could have different orientations. Could be standing, but could also be floating at different angles like this, as you would expect in space. And the goal of the experiment was to ask the other character behind the shelf to give an instruction to the subject. So me as the subject, I'm seeing the scene, and I see a person kind of maybe oriented like this, and the person tells me, can you move the object, which is at the top of the shelf, towards the right? And so because those verbal cues are in the reference frame of the person behind, which might be differently oriented, I have to make this rapid computation in my head of reorienting everything for me. And so that's what we tested first on Earth, just to get some baseline data of how people do this task. And then we also did it in a parabolic flight.
So you recorded how long it takes for the subject to do this mental transformation?
Exactly. We recorded both the reaction time, so how long it takes, but also how accurate they were. Were they actually picking the right object and moving it in the correct direction?
Cool.
Yeah.
And so you did that on Earth, and then you did the same thing in microgravity. How do you simulate microgravity?
Yeah, so there are really only maybe one way. For the experiments that I just described, is really only the parabolic flight. Basically, you can imagine a plane following a series of parabolas. The plane will tilt like this, and then at some point will start going down, and then it will fall down exactly following the acceleration of gravity.
So you put yourself in a falling plane.
Exactly.
You're crazy.
Yes. So yeah, we were falling, everybody was falling. Yeah, so I mean, so something I wanted to mention about parabolic flight is that it's fun, of course, for us experimenters, but it's also very challenging scientifically, because you can imagine that usually when you do a scientific experiment, you want to be able to control all the variables in your experiment. The issue with parabolic flight is that it's not only the factor that you're playing with is not only gravity, but you're also playing with people's stress. You're also playing with a lot of noise because in the plane there's a lot of noise. So all of these factors, you have to take those into account when you make a scientific claim. What I mean by that is that if you see that performance changes in a parabolic flight, you cannot just simply say, well, that's because now they're in microgravity. Maybe it's because they're in a plane or because they're stressed. So we had also sort of designed the experiment to have some control conditions where we knew or we expected no differences in performance if people were doing it on the plane.
So before we talk about the results, what were you expecting when you designed that experiment?
So we were expecting that people would become worse at performing the task once they are weightless, if you want. That was because we knew from the literature that other people have done similar experiments, and some people have seen decline in performance, and interestingly, a few people had seen the opposite.
So what were the results?
So the results were opposite to what we thought.
Okay.
What we found was that actually people did better.
Wow.
And by better, I mean they were slightly faster in microgravity versus on Earth, or even in the plane when there was no microgravity. And we were kind of puzzled by this. And as I said, we had those conditions, simple conditions, where basically the character behind the shelf was not tilted. So there was no really mental rotation to do. And when we compared the performance on those conditions between 1 gravity, 1g, and 0g, 0 gravity, we didn't find any difference. So that told us that it's not something that which might be related to stress. We only saw increase in performance on conditions where the character behind the shelf was actually tilted.
Ah, okay.
And so what we interpreted, and this is really an interpretation, we don't have a really way of proving this, but what we thought was that maybe because this tilt of the character becomes possible, physically possible in weightlessness, in a microgravity environment, maybe the brain now is able to imagine this position. Whereas on Earth, because it's impossible to imagine someone standing at 45 degrees, you can't possibly, or it takes maybe more time to imagine this situation. Then when it becomes actually possible around you, maybe it becomes easier to imagine it.
What's next? Do you plan to do these experiments in the International Space Station?
So I would say that this would be the dream experiment, although I think it takes really a long time to send anything on the ISS. So I think the next step would probably be to reiterate our study to prove our results.
So we forgot to mention that the pilot of the plane where you conducted your experiments is someone famous, right?
That's true, yeah. So we did, actually with my team, we did 2 parabolic campaigns, and on the second campaign, the pilot was Thomas Pesquet, the French astronaut, and he was actually passing his pilot license, not just like a regular license, but really to fly those parabolic flight planes.
Nice.
That was very exciting.
That's really cool.
Yeah.
So in the age of robots and computers, what's the point of sending humans into space?
Yeah, so I was prepared for this question. I think there is one answer which has been used, maybe overused, but I still believe in, which is that sending humans has some inspirational aspect to it. I think a lot of us scientists, we tend to think of space as a science mine, like something you can mine to get some data. But it's also, the other aspect of it is also exploration. And exploration means motivating others to go even beyond and beyond. And I think doing this with robots is much harder than doing this with humans. So that's the first answer, which I think I haven't said anything that anybody has heard before. It's really well known. I think personally, the strong belief that I have is that sending humans is so difficult that it kind of poses challenges which are important to solve. Not only to solve to go to space, but also then it can be applied to on Earth. And so I think going into this very harsh environment helps us think through solutions that we may not be able to think of if we were just solving issues on Earth.
Mm-hmm. Yeah, for instance, we can mention the water treatment system that were developed for astronauts and that are now used for developing countries,
Exactly.
Countries where they lack water.
Yeah, there are a lot of spin-offs like this coming from people doing research for space that now are being applied for Earth. Yeah.
If given the chance, would you go to space?
I think so. I think that I would love to just. I think there's just the thrill of being in that environment, but I think it's also really a cool job. To be an astronaut to me means knowing medicine, knowing engineering, knowing science, and I think this is basically what I've tried to do during my academic path, and I think that would be the only job in the world that would allow me to tap into all of those disciplines at once. So yeah, I would love to do that.
How is your vision for the future of space exploration? Should we go back to the moon? Should we follow Elon Musk and colonize Mars?
I think so. Yeah. Again, I think these are more emotions rather than hard evidence for what I'm going to say. But my personal view is that we should take it slow, and I think we should not rush necessarily to Mars. And I think going back to the moon is probably a good idea, even though people are skeptical and saying, what is the point of going there? Because we went there. But I think when human lives are at stake, I think it's really necessary to make sure we know all the different steps. And NASA is known, and other agencies are really known to be careful. And I think they should really continue that path.
Cool. Well, that was all very interesting, Nico. Thank you so much.
Thank you for the invitation.
So you're defending your PhD very soon?
Yes, that's right, in the summer. Yeah.
Cool. Well, good luck with that.
Thank you.
I'm sure it's going to go very well.
Thank you, and thanks for the invitation again.